Okay, so we will continue with an example in Cadence, and for example we will have a common source amplifier. So our common source amplifier is here, and I have two versions of this common source amplifier. The one at the left, it is a self-bias transistor, NMOS transistor that it is connected as a common source amplifier. So we can see here that the input voltage is located here in V4, gate to source voltage is V2, the drain to source current, it is here I1, and the drain to source voltage, it is V3. And then I am loading the drain of this transistor with a resistor of 9 kilo ohms. Okay, so this is the circuit that we are going to test, common source amplifier. And the same circuit, after we perform, after we bias it, we find the suitable biasing circuit for this amplifier. It can probably look like something like on the right. They have the power supply, we have a current mirror, and then we have a transistor and the load connected to the power supply. So we're going to discuss about biasing techniques later during this course, so let's just assume that this is the way that we decided how to bias this circuit. So I will show you the example with these two alternative circuits, because then you will appreciate how handy it is to be able to extract the static nonlinearity very early during the design. So extracting the static nonlinearity can be done already with a self-bias transistor, as we see in the left. What we have to do is only to sweep the input voltage as a DC quantity, the DC input voltage, and then check the output voltage. And after that, we can extract all the errors that we need to do a first estimation of nonlinearity. If we don't do it this way, we will have to rely on a circuit that it is almost finished, a circuit in which the biasing has already been implemented. That happens pretty much later during the design cycle. And if it doesn't meet the specifications, then all the effort that we spent during biasing will be basically in vain, because we will have to do it again after we fix the nonlinearity problems. So that is a very important aspect of trying to extract as much nonlinearity information as possible very early in the design, namely when we have just self-biased transistors. You can imagine that I can use here the ADL or ADXL, and actually there is a template in ADXL here available for you. We're going to open it very quick. So there is a template that it is going to run both a DC sweep and a transient simulation to basically compare the results of nonlinearity taken from the differential gain, or nonlinearity taken from transient simulation and spectrum analysis. Doing it will require basically to set a number of equations to extract the errors, and then extract the D2, the distortion of second order and third order. And this is exactly in this kind of situation that it is much more handy to do Ocean script, to perform these same tasks using a script. So I instead use the ADE to generate a very simple script for this simulation setup. And in this script I will run a DC and a transient simulation, and I will basically derivate the output voltage that we have here, the output voltage, in order to get the gain. After the sweep simulation, VS is voltage sweep, and then I just get the different points of gain. So we will get the derivative at 0, the derivative at 10 millis, and derivative at minus 10 millis. So this is under the assumption that I will inject a signal with 10 millivolt amplitude. Okay, so I will start checking what is the error if I move to a maximum amplitude of plus minus 10. And yeah, I calculate these errors, and then I can immediately calculate the distortion of second order and the third order distortion also, and it just present the results. At the same time, I'm running a transient simulation with a conservative to get a very good, let's say, very low error during the transient simulation, very accurate points. And then I will plot it because I will want to work with the spectrum analyzer in the plot tool. So let's run this script. Control Alt, Control Lima. We run the script. Then after it finishes, it gives us as a result that the intermodulation, the second and third order distortion values obtained from the DC sweep are minus 42 dBs and minus 65 dBs, just by using the equations. And then let's take a look at what happens if we check the transient simulation. The transient simulation, it is taking the output from the bias circuit. Yeah, it is taken from the circuit in the right, that it is the final circuit that it has been already designed with bias included. And then let's take a look what it is the nonlinearity. So we can go to measurement, we go to spectrum, and we're going to leave it exactly as it is, all the parameters, and then we put the spectrum in a new window. So we plot it here. Let's sum the main harmonics. So we take a marker in the fundamental, we take a marker in the second order distortion located at 2 kilohertz, and then we can use a delta marker. And then we see that the second order distortion, it is located 43 dBs under the fundamental. And the prediction from the static simulation is 42. So it is very, very close. I mean, this works very nice at low frequencies where the capacitors are not affecting the intermodulation distortion. We will take a look about the capacitors later when dynamic nonlinearity is studied. Let's take a look to the third order distortions. Then we move to the next harmonic, 3 kilohertz. Then we have that the third order distortion is located almost 64 dBs under the fundamental, and our equation predicts minus 65 dBs. So again, the distortion levels that our static simulation is showing us are very, very close to the results that are provided by transient simulation and spectrum analysis. So we can really trust the method. So to extract the static nonlinearity, or nonlinearity at very, very low frequencies.